Okay. Oh, I'm not seeing anything. Full screen. My video panel. Yes. Okay. So, we finished the first two chapters of the course, fields and numbers, and I and linear system of equations and solving them via matrices. Okay. So we're just starting. I'm just stating that we finished the first two chapters. The first one was the fields and numbers that included specifically the complex numbers. And after that, we did a segment about linear system of equations and how to solve them using Gauss elimination. The next chapters, plural, I will tell you all of them. The next chapters are algebra of matrices, vector spaces, and linear transformation, which are linear functions. Okay, so it's beginning to become, yeah, it's beginning to look like a horrible Christmas. It's beginning to look like linear algebra. The first two chapters are, well, they have different flavors to them. The fields and number were accurate definitions of fields, and also we learned about the complex numbers. Well, sometimes you learn about it in high school and it's enough, sometimes not. And I made sure we know what we need. The linear system of equations and solving them through matrices is the technical tool which we use to solve the algebraic problems, like intersectional plane. That's a geometric problem, to be honest. But what I'm saying is that linear system of equation for me is rather a technical tool than an abstract concept. And now we're continuing or getting to the algebra of matrices is a lot more like fields, the abstract definition of a field. And like I said on the first day, the main purpose of linear algebra is to study linear function between vector spaces. And if you can see here, these are exactly the last two chapters. So these are my point. And I will just say one more thing before I start. Remember, linear functions are matrices. It's not a mathematical claim. It's not super accurate because the full sentence should be linear functions over vector spaces with finite dimension. But that's less catchy. But linear functions are matrices. So when we learn about the algebra of matrices, we learn some technical tools to work with algebras. That's the technical part. but we are actually starting to learn about linear functions. And as a part of the introduction, I would like to give you one example. I think it helps to understand a bit of what I'm saying. Example, look at the rotation matrix. So what is the rotation matrix? Cosinus theta minus sine of theta, sine of theta, and cosine of theta. Let's
It's not minus.
no. Are you guessing or remembering? Because I'm pretty sure I did
remembering,
twice.
but maybe I'm just
Okay, so
wrong.
let's make sure. Where did you see a rotation matrix before?
In-
Oh, really?
yeah,
Weird. We don't have matrices in high school at all.
I took an extra mathematics.
I see, but I was
Okay,
right. Okay. And
Then you put this in.
that's fine.
no, sometimes you can do another minus and then it's a rotation clockwise instead of counterclockwise. Maybe it could be that, but I just did it a few days ago, so I ought to remember. It is confusing because cosine and sine and plus or minus. So what is the rotation matrix? If some of you seem surprised, you're not supposed to learn it in high school, right? So first of all, it's a matrix, right? What have we seen about matrices up until now? There were a representing of the coefficients and the scalars in a linear system of equation. This matrix has nothing to do with equations. I'm not looking at the equation cosine of theta times x minus sine of theta times y equals 0. No, it's not what I'm doing at all, right? So what does this matrix do? It's called a rotating matrix, and because it rotates, and when multiplying by this matrix, we can rotate vectors in the plane, as we shall see later. So you're not expected to know why is that a rotating matrix. You're not, by the way, but by what angle does this rotate? Theta, obviously. So you're not supposed to know why this is a rotating matrix, and you're not even supposed to know what does it mean yet. What does it mean to multiply by a matrix, right? That's the chapter is algebra of matrices. We learn how to do operations with matrices. The addition operation is quite trivial and natural. The multiplication operation, however, is kind of weird. I'll try to ease you into it and explain to you why does it look the way it does, but it's a bit weird. So you're not supposed to know why is it a rotating matrix, and you're not supposed to know how do we multiply by it. But I do wish for you to understand why this means that the matrix is sort of a function. When we multiply by this matrix, we're applying some kind of operations. We will also see later that there exists matrices that when we multiply them, we multiply by them, and it's applies what do I call it in English? I don't remember. Elimination operation?
Of what?
The three פעולות הדירוג. Elimination operations. I look for it. I don't remember how I.
You mean it shortens it collapses it by a dimension.
No. These elimination operation. Yeah, that's what I said. And when we do Gauss's elimination, we have three operations. We can add a times rj to ri. We can multiply a row by a constant, and we can switch the places between two rows. Each of these operations has a matrix that when we multiply by this matrix, it applies the operation. Again, we need to, I wish for you to understand, it applies an elimination operation. So matrices can apply
Transform.
yeah, changes just like a function does. The other side of this coin will be to prove that any linear function can be replaced by some matrix. And that's why I say matrices are equal to the functions, okay? But we need to think about the matrices and their algebra as function. Why is it so important for me? I'll give you an example. Say you have a function f that receives people, and its domain is people, and it sends out its image or range are cats. Say you have a second function which receives cats and oops, not cats, cats, and outputs names, the name of the cat. And when you apply people, it outputs its cat. Okay, I didn't say what is the range of definition, domain of definition, but fine. Okay, so given these two functions, what could be the natural operation to do between these two functions? Can we sum them up? Can I say f plus g? Does that make sense?
No.
No, because in order to do a plus, I need the domain to be the same, right? Because I need to take some element, put it both in f, then in g, and then sum up what comes out. So addition is not a natural operation. What is the natural operation between f and g in this context?
You're sure?
What's sure?
Like doing one and then doing
Yeah,
the
so
other.
what's the name? You're supposed to know it. You learn it in discrete mathematics, I think. Composition, exactly. So, and the natural operation between these two functions is composition, meaning applying one after the other. Does the order of composition matter?
Yes.
Definitely. Agreed? Because if I say g of f of Sammy, do you have a cat?
I have a dog.
Yeah, okay,
Nice.
so for Sammy, I'm changing the questions. Okay, so g of Sammy, f of Sammy, sorry, would be its dog, And when we put Sammy's dog into G, it will give us his name. So what's Sammy's dog's name?
Bisley.
Beasley? How do you spell it?
BISSLI.
L-I. Oh, Beasley.
Yeah, like
Oh, okay, okay.
Like
Beasley.
flag.
So, Sammy's dog is named Beasley. But can we do a f of g of, I don't know, some dog? Some dog, I don't know. No, because then it would be f of, let's write not some dog, let's put Sammy's dog. Sammy's dog. So, we'll get f of Beasley, which makes no sense because f is supposed to get people, not names of pets. Agreed? Okay, you will see in a minute why is it so important. Another example, take normal functions. Cosine of x, f equals sine of x, and g equals x squared. These are two functions. These are two real functions, meaning from the real numbers to the real numbers. And so now we can compose the, I didn't write here that this does not make sense, right? We can compose the functions in the two different orders. And will the result be the same? With this f and g, one of the function is sine, the other one is x squared. I can compose these two functions in both orders, first f and g, or first g and then f. Will the result of these two compositions be the same?
No.
No, it would not. F composition G of x is f of g of x, which is sine of x squared, but g composed on f of x is g of f of x, which what does it equal to? It's g of sine x, first of all. Do you agree about that? And what is g of sine x? G takes whatever you put into it and squares it. So it's sine square of x, right? These are not the same function. For instance, sine square of x is always positive. And sine of x squared could be both positive and negative. I'll draw it to you just to make sure you see it's a different function. These are two different functions altogether. I'll show you the graph. Graphing. Close. Don't save, I didn't change anything. Okay, so look at sine of x squared. Looks like that. Sine of x squared. Hate this noise.
maybe it's a door.
Probably.
So sine of x squared is the red function. You see all different functions, two different functions all together. And what does it all have to do with matrices?
Because we can do operations in different orders and expect the same result.
Not just that, it is even more than that. What does all that have to do with our subject. It's a rhetorical question.
Can I ask a tangent question?
Yes, okay.
With functions, if the range is exactly the same for two different functions,
Yeah,
but using it in different ways result in the same.
that's exactly what we have here. Your
No.
range of R and R. Ah, you mean because the image, not the
Sorry,
range.
the image, that's what I meant.
No, it doesn't
No.
matter. It doesn't matter. It doesn't matter. Composition is not, it's inherently not commutative. An example I like to give when I teach discrete mathematics. Here I tell you about composition because it has to do with matrices, but it won't be as complex because we all only consider linear functions. But in discrete mathematics, when I teach the entire things, I always say, if you have a baby and you have two operations, one is making him open his mouth and the other one is feeding him. Does the order matter? Yes, right? It's not just about the range and the domain. It's when you apply two different operations, the result very often differs by the operation you apply them. In general, it's a general mathematical, I don't know, concept or fact, whatever. So what does it all have to do with our subject? And the multiplication of matrices that we will define and study represents a composition of the linear functions that the matrices represents. Therefore, the order of, I'll rephrase myself, the multiplication would not be commutative. It will matter commutative. It will matter which matrix is on the left and which matrix is on the right. And we will not be able to multiply any two matrices by any order. Like we've seen with the function, the first example with the pets and the people, we could apply the composition in one way, we could not do it the other. With matrices, it would be the same. Sometimes we can multiply A by B, but we cannot multiply B by A, okay? So understanding this multiplication, so-called multiplication, is actually composition, helps us understand why is it so different than the multiplication with numbers, right? Because then it was commutative and we have closure, meaning every two elements you can multiply by every which way and it will be defined. So in matrices, it won't be the same because matrices are actually functions. It will take us some time until I be able to prove that matrices are actually functions, but it helps to understand from day one that that's what happens and that what is multiplication. That's what multiplication. For instance, another example, and I think after that I will continue with definitions and formal claims. And so last example, I think, let's assume given the rotation matrices R theta and R alpha. What do you think the product is equal to? If I multiply R theta by R alpha.
what are rotation matrices?
Yes.
Um,
Alpha theta is a rotation matrix that rotates by angle theta. Alpha rotates by angle alpha. So what do you suppose the multiplication of these two matrices will do?
It's rotation by theta plus alpha.
Exactly. Rotation by theta plus alpha. Because it's a composition. The multiplication is actually a composition. It says first rotate by alpha, then rotate by theta. Obviously, geometrically, we understand that that means that altogether we rotated by alpha plus theta. And it's actually true. Okay, if you take both rotation metrics and multiply them using trigonometric identities, we can prove that that's actually the case. But again, I'm just trying to get you into the mood of what we're trying to study here. Okay? It will also be a result of some theorems that we will have that will prove that the multiplication is like composition, but this will take time. Understanding now that it's true, that doesn't take time if you just believe it. Okay? Any questions so far? Yes.
this is derived directly from the trigonometric functions, or is it?
The proof in this case, yes, but the general proof that shows that the multiplication is actually a composition is another way to prove that it's ought to be the rotational matrix like that, right? And the direct proof is like you said, I just take the two matrices, I calculate the multiplication according to the definition of multiplication, which I haven't shown you yet, right? And using trigonometric identities, you see it's actually the case. But for me, this proof is less interesting than the fact that it works and understanding the concepts behind it. Okay, so that's just a composition of two rotation matrices. Okay, so we will start with a few definitions. First, given a matrix A of size m times n, which means it has m rows and n columns.
F stands for field.
Yes,
What matrices on it?
I never wrote to you this notation yet.
I think so, but maybe you
Let me just make sure if I didn't write it, then I
Maybe you
ought to
define it.
define it well. It could be, but
I think you did write it.
yeah, I just make sure and then I'll answer your question anyway. I won't tell you I wrote it and ignore you. I wish to know whether I wrote it or not. Where did we start? Learning matrices. Here, yes, I did. Here, definition. Given a field F and the natural numbers m and n, we define f m n. It's not just f, it's a whole syntax, which means the set of matrices with m rows and n columns. Okay, so A is a matrix of number. The numbers come from the field, right? But it's a table of matrices, like a two-dimensional array in computer science, with m rows and n columns. So given a matrix M and given I between 1 and M and J between 1 and n, meaning that we're getting a number of a row and a number of a column. We define A I J to be the element in the matrix at row number I and column number J. Note, sometimes we will write AIJ for short. Instead of going with the full brackets, sometimes we just write a smaller a. Let me give you an example to make sure we're all on the same page. Example, if the matrix A is as follows: 1, 2, 3, 4, 5, 6. So the elements 1, 2, what would it be?
It's 2.
Yes, because it's the first row and second column. Okay, and in the short notation, we'll write A, 2, 3. What is that?
6.
6. It's quite important because I need some way to mention a specific element of the matrix, and that's the way. In computer science, the way you would write it, note, in programming languages, one would write A at 1 at 2, right? More horribly than that, because of zero count, we write A01, right? But it's just a matter of the syntax, right? So in mathematics, that's the way we write it. We have, by the way, what is one of the reasons that for such a big change? Because mathematics was there before computer science. Why is the programming language so different than how mathematicians wrote it?
Because they think about it wrong.
No.
Zero.
I'm not meaning zero count.
Ah,
Forget the zero count. I'm just meaning syntax. Why would they write a brackets 0 brackets 1 when we just write a 1 comma 2? And the reason is that subscript is not easy to write in computers. Nowadays, the fact that I can do this in Word is pretty modern, okay? And you used to have ASCII tables, and you can just write characters one after the other. So they invent some ways to write it, which is easier than, which is harder. I don't know, it's harder or easier. Which was hard to write the things we wrote on paper in the computer. So some of the syntax is different, but it doesn't really matter. I'm just saying that for your brains to make a connection. That is basically what I'm saying. I'm getting into a specific element of this two-dimensional array. And now I can define a definition, addition, and multiplying by a scalar of matrices. So definition, given two matrices A and B of the same size, we define A plus B to be a matrix of the same size as the two matrices we have by the element of A plus B in row I and column J, what it would consist of, it would be the sum of the two elements of the matrices in the very same place. Does that make sense to you? That's the general definition. I will give you an example. Take, I don't know, 2 by 2 matrices. Matrix ampersand plus the same size matrix. The result would be the same size matrix. So if this matrix is 1, 2, 3, 4, and this would be 5, 6, 7, 8. The result matrix, what would it be? 6, 8, 10, 12. Agreed? What is important for me, for you to understand, is that what's written here is exactly what I did in this example. I told you, if you wish to know what is the number here, I told you, just take the numbers in the same place in the two matrices and sum it up. That's natural, that's not confusing. It's all counter to multiplication, which will not be natural at all. Some would say unnatural, but okay. And next definition, multiplying by a scalar, given a matrix A of some size, I don't care, and a scalar C from the field, we define the matrix C times A to be a matrix of the same size as the original matrix by C times A in the place ij. What would it be?
C times
C
Aij.
times the original element that was in the matrix, basically multiplying the entire of the matrix by the scalar C. I'll give you another example of that. Another example, and it will be of that. So I can use the very same matrix, take this matrix, and I don't know, multiply it by some number, -1 times the matrix, and we will obtain -1, -2, -3, -4. Agreed? So far, it's supposed to be not confusing. Okay, the addition of matrices is easy, the multiplication by a scalar is easy. The multiplication of two matrices, that's where the money is. Okay. And last, introductory example for multiplication of matrices. So what we've seen so far about matrices was, not today, before I mean, was to use it to solve a set of linear equations. And that would be in my example. So if I have x plus y minus z equals 1, and I have x plus 2z equals 2, the coefficient matrix is 1, 1, -1, 1, 0, 2. The column of the variables is x, y, and z. and the column of the constants is 1 and 2. We wish that we could represent the system using A times X equals B. What does it mean? A is a matrix, but also X and B, right? This is a column, one column, 3 rows. It's a matrix as well, right? So I wish to multiply the coefficients by the variables, so it magically become the left-hand side of the equations, and then take the whole thing and demand it will equal to the coefficients 1 and 2. That's what I wish to happen. But for now, it doesn't mean anything because that's a multiplication of 2 matrices, and we still did not define it. But I'm using this example as the first example of why does the multiplication looks the way it does. Okay, so we wish that the coefficient matrix times the variable column will equal 1/2. So first thing I wish to say, I don't know if you feel it as well, but it's a bit weird to multiply such weirdly shaped elements. We are used to multiply the same kind of things, 2 numbers, one by the other. But now I'm multiplying 2 matrices and they both have very different sizes. But why does it make sense? Because multiplication is actually composition, and like the example with the people, the cats, and the names, it can be weirdly shaped. Every matrix will have a different domain and range, domain and range. Okay? There has to be something common between them to be able to compose them. What is the common size between these 2 matrices? 3. It's the number of columns here and the number of rows here. That will be one of our requirements, that the number of columns of the left-hand matrix will be equal to the number of rows of the right-hand matrix in order to be able to do multiplication, which is the same as when composing 2 functions. I needed the range of the inner one would equal to the domain of the outer one. And in the example I gave, it was the pets. Okay? And now I wish the coefficients to meet the variables. This coefficient, which variables should he meet? X. And this variable, Y. And this variable, Z. So it looks like this. I'm taking a row here and multiply it by a column here. Okay? And after I multiplied, after I've given each variable its coefficient, what do I do with all of this? I get 1 times x and 1 times y and minus 1 times z. And what do I do with the 3 results? Sum them up in order to get this, right? It's x plus y minus z. And that exactly will be, and you will see the multiplication of matrices. I take a row from the left-hand matrix, multiply it by a column of the right-hand matrix, and I sum up. I multiply element by element, and I sum them all up. I will obviously write this as a definition, but I wish for you first to get it now. So I will use colors. So the yellow one would meet the yellow X, and the green one will meet the green Y, and the turquoise, it's actually cyan, and one will meet, it's not turquoise, oh, anyway, will meet the cyan Z, and we'll sum them up, meaning that the multiplication of, we will see that the multiplication of these two matrices is x plus y minus z, and the second element here is 1 times x, which is x. How many times y? 0 times y, and 2 times z. So it's x plus z. And there, and now ax equals b is actually equivalent to the linear system of equations. Okay, so far? Yes, sir.
It's 2Z.
Oh, thank you. Susie. Any comments, questions? Okay. So now one last thing I need to make sure, it's a recap or reminder. If it's not, then tell me because it's quite important. When I write the sum from 1 to n, oops, forgot to write the variable name. From I equals 1 to n, and excuse me, I will change if I is not a good name here. P from 1 to n of AP. Have you seen this notation before?
For the sum,
Yes.
Mhm.
So it would be I substitute instead of P all the numbers between 1 and n, and then I sum up all the results, meaning A1 plus A2 plus AN. Does this notation make sense for everyone? Because it will be quite important. Why? Because that's actually the basis of multiplication of matrices, because I will multiply one element by the other and one element by the other, and then I will sum them up. So I will have to use the sum a lot.
what is P in this?
It's not really, it's the index of the summation, right? You don't need it by the end. I'll give you another example. It's like, again, from computer science. We'll do it. What does that mean? And I will write it in Python. I wanted to say actually a programming language, but I will do it in Python. So the sum is equivalent to the following thing. Define A of P, some function, return something. Let's just say for now it's P. Okay. And now I'm doing a for loop this way. Sum, I don't remember how you do for loops in the sum.
For I in range.
For I in range, yeah, it's formula. For P in range n, and I need some n. I leave it like that. I don't need to compile it. And then I write sum plus שווה, plus equals, sorry, I went Hebrew for a second, A of P plus 1. Okay, the zero count is annoying, but in this case, but do you see? Right, P is just the index of the for loop. It doesn't have anything by itself. It's just a placeholder in which you substitute all the numbers in the range. Agreed? That's exactly what is written in the mathematical notation, sum. So, in Python, it looks like this. And it is important. It's like the index in the for loop. And I will, why did I take I out, not an I out? Because I usually is a certain row and J is a certain row and N, M, and K are usually the size of the matrix. So the index need different letters. Usually we go P, Q, R, something like that. But it's just a placeholder, right? The important number here is N and the element of the, I don't know, unknown sequence A of P. These are important. The P itself has nothing here. Okay? And I will do another example that will help, I hope. And say we have the matrix A and we wish to multiply it by the matrix B. And we wish to look at the element in the first row and the first column. What would that equal to? That's the question. I wish for us to get the answer together. So even though I didn't define multiplication yet, just by what I explained so far. So assume A is this matrix. I'm not saying what is the size, it's just a regular metric, some size matrix. And B would be another some size matrix. And therefore the result must obviously be some size of a matrix. Okay, and I'm not saying what are the sizes, okay? But I wish to know what is the element here. So by what I told you about, I'm taking a row here and multiply it by a column here. Do you agree? What is the name of the element here? How can I refer to it? This matrix is called A, and this matrix is called B. So what would be the element here?
Base of 1, 1.
A1, 1, exactly. So this will be A1, 1. Agreed? The next element would be A1, 2. I need to increase the matrix now, I see. Insert column after. Here I will insert a row. You will see field Y, see dots. And what would be the last element? It will be A, comma,
And
who knows? The size of the matrix, right? Let's go with N. What does that tell us about the size of this matrix? What can I write here? Well, I don't. Writing here is a bit of a shorthand, but I like to write next to the matrix its size at the start when we don't fully understand. So what would be the size of this matrix? What times what? How many rows does it have?
M, sorry.
Yeah, we don't know, so it's some M, and the number of columns is N, okay? Okay. What is the name of the element here?
What's the name? It's B11.
It's B11. So far it's the same. But where should I go next?
To the bottom.
Yeah, on the way to the bottom because I'm multiplying a row by a column, right? Like these are coefficients and these are the variables. In general, it's not the only story. Like I told you, the matrices have many other stories than that, but that's the story now. So below B11, what is the name of the element?
B21.
B21, exactly. B dots. And what is the last element here?
BN1.
It must be n. It must be the same n. Otherwise, I cannot do the multiplication because I need them to match. I need an element for an element. Agreed? And how many columns does the right matrix have? We don't know. So it's n times something. Okay. What would you guess that the size of the result matrix will be? When I'll get to the definition, I will write it to you. Just so some lectures like to start with the definition and then explain it. I rather start with the explanation, then give the definition, then students actually understand it. But what do you think the size of the result matrix will be?
K times N. M, sorry.
M times K. Okay, and think about it as composition. These are people, these are pets, these are pets, these are names. So what enters are people, and after the composition, what comes out are names of pets. This is the same. And you have to go through the common size or common set. That's the idea behind it. And now what the element I'm talking about here should be written here. So what would it be? A11 is multiplied by who?
Oh, 11, B11
B11, right? Row by column
plus
plus A12, which will be multiplied by
B21.
B21. Add colors. So the yellow element is multiplied by the yellow element. Green element will be multiplied by the green element, so forth until last cyan element will be multiplied. So A1N is the last one. Who will it be multiplied by? Last element here, BN1.
By B1, A1
And plus A1N. Fine. 5 times here. A times B and 1. And now I wish to write it as a sum. So it's sum from P equals 1 until N of what? What should I write here?
A1 B times B1.
Exactly. B, B1. In a few seconds, I will actually write the definition of multiplication, but I wish for you to appreciate it first. But that's exactly the idea. And notice that what does this one here represent?
Oh, row.
It represents that we took the first row of the A matrix. What does this one here represent? That we took the first row of the B matrix.
The column.
The column, thank you. Did we have to take the first row and the first column, for your opinion? No, we could have taken any row of A and multiply it by any column of B. Therefore, in the general case, instead of 1 here, we will write I. And instead of the 1 here, in the general case, we will write J. And it will be the row and the column of the element we are currently calculating. And after saying all that, we are ready to the formal definition, formal general definition. Definition. Given a matrix A of size m times n, and another matrix B of size, n times k, and I wish to emphasize that the n here must equal to the n here. Otherwise, the multiplication will not be defined. And we define the product, the product AB to be a matrix of size. What's the size of the product?
Outer size, so m times k.
Exactly, m times k by the element of AB. Usually we won't write the dot, but for now I will. The element of AB in row AI and column J is basically the multiplication of the I row of A by the J column of B. I'm putting this within brackets because it's a circular definition, because we don't know yet how to multiply these two, because these are two matrices, right? But it's important for you guys to understand it. I always take a row from the left-hand matrix and multiply it by a column of the right-hand matrix, and the I of the J in the product say which row of A and which column of B. And the definition is the sum from P equals 1 to N of A, I, P, B, P, J. I hope you appreciate now why I did so much introductory before showing you guys this. Not sure it helped, but this is scary. This is scary definition. However, it's not really complicated. I think it's just like looking at some program some other guy programmed before you. So it looks scary a bit, and if you read it slowly, you understand slowly what he did. So that's kind of thing. It looks scary, but it's not really complicated. And I will give you examples in a few seconds. Yes.
We have to specify that I equals J.
It doesn't have to equal. Oh, any row of the A matrix by any row of the B matrix. It could be different. I just gave you the first example, first row and first column, but it could be any row, any column. Okay, we'll see examples in no. Okay. Example. So take a matrix, give me a random size. How many rows?
Your
4 rows, that's huge. How many columns?
2.
2. Okay. So that's the size of the left-hand side matrix that Thomas has chosen. Now, what would be the size of the second matrix? How many rows? No.
Rows.
How many?
Sorry. Rows 2.
2. It must be. Why? Because the number of columns of the left-hand matrix must equal the number of rows of the right-hand matrix for the multiplication to work. The other two numbers are random. So I'll choose the last random number 3. 1, 2, that's 3. And we can multiply these two matrices. Can we invert the order? Invert the order of the matrices? No, because this has 5 rows and this has 3 columns. So it won't even be defined if you try to multiply it on the other way. And what would be the size of the result matrix? How many rows? How many columns?
4 times 3.
4 on 3. Said 5 before, but it's 4 rows. Yes. So now I'll write the sizes up here. At the start, it's important. 4 times, it helps, not important. 4 times 2. And this is 2 times 3. What's important here is the 2 that is equal number of columns of the left-hand matrix must equal to the rows, number of rows of the right-hand matrix, and the result is of the size 4 on 3. 4 rows, 3 columns. Now I will populate the example with numbers. 1, 1, 0, 1, minus 1, 2, 0, 0, 1, 2, 0, 0, 3, 3. Okay, just random numbers for us to be able to calculate. And I'll remind you of the website Matrix Calc.
I used that today.
It helps. Matrix Calc, and we can put the matrix here 0, 1, minus 1, 2, 0, 0, and the next matrix, which is 1, 2, 0, 0, 3, 3, and we can multiply and get the actual multiplication. So again, you should use it after you are sure that you are able to do it by yourself and you're just saving time, because in the test you won't have the matrix calculator. So this is the result, but we didn't get to it yet. How many elements do we have here on this matrix?
What do you mean? How many?
How many places?
12.
12 numbers, right? We won't do them all. It's a kind of a waste of time. Maybe we'll do 2 of them. So let's start with this one. How can we calculate this specific element from the entire product? So what does this tells us? This element, what is its location? It's 2 and 3. Agreed? It's on the second row, third column. That means that the I in this formula is 2 and the J is 3. Here it tells us multiply the second row 0, 1 by the third column, 0, 3. And how do we multiply them? 0 times 0 plus 1 times 3. So what is the number that's supposed to be written here?
3.
3. And I'll write on the computer what I just said. I take the second row here, multiply it by the third column here. Why? Because I wish to get to this element. And I take the rest of the column, a row, sorry, and multiply it by the rest of the column. And I get 0 times 0 plus 1 times, nope, times 3. And we can multiply any row of the left-hand matrix by any column of the right-hand matrix, and each choice for a column and row, each 12 choices for a column and row have a space in the matrix. Let's take a second example here. This element. Okay. Who will I multiply by whom in order to get this element?
That's 1, 3. So it's
It's 3, 1. Third row, first column. So I need to multiply the third row by the first column. So it's -1 times 1 plus 2 times 0. So here it should be 3, here it should be -1, and now I can go back to the site and you can see the 3 and the -1, and you can see it always works. So this, for instance, is 1, 1. When multiplied by 2, 3, we get 5. So it's 1 times 2 plus 1 times 3, and you get 5. Agreed? So that's the definition of multiplication of matrices. Next example, interesting one for me, in my taste. Example, take a general vector in the plane and B equals AB. And do you care to guess by which matrix I will multiply?
Sure.
No, whichever.
No, I mean whichever it has
No,
2 rows. No.
it's not that you're wrong. It's just we'll multiply it by which matrix? Multiplication of the rotation matrix and the vector. So R theta times B equals to and cosine of theta minus sine of theta, sine of theta, cosine of theta, okay, times a b. First of all, is the multiplication defined? What is the size of the rotation matrix? 2 by 2. What is the size of this vector?
Of the original vector, it's 1, 2, or not 2, 1, sorry.
2, 1. Right? 2 rows, 1 column. So it's defined. And the result would also be 2, 1, which is also a vector, which is good. Agreed? How can I calculate the elements here? Let's say the first element. Whom should I multiply? Whom should I multiply by whom?
First column by the
First row by the only column, but yeah, the first column. So it's cosine of theta times A minus, because it's minus sine, minus sine theta times B. And below, it's sine of theta times A plus cosine of theta times B. So we got one vector in and one vector out, like I said, a function. Okay, we got an A, B as an input, and the output is this vector. And supposedly, the result vector should be rotated by angle theta. And we'll make sure that's actually what happens. So clear all, discard, and choose a random A and a random B. And look at the vector AB. Now choose a random theta, and I will call theta P. Okay, so P would be, I don't know, pi over 4. I'll start with that. And now the second vector ought to be cosine of P times A minus sine of P times B, comma, sine of P times A plus cosine of P times B. And now when I write the angle between B and U, that's not what I wrote. Angle between B and U. Great. Aha, 45 degrees, which is exactly pi over 4. And the interesting thing is, let's change A and B. What do you see happening?
the angle is the same.
The output vector is always the rotation of, it's not just the angle, right? It's the length as well. The output vector is always the rotation of the input vector by the same angle. Let's switch pi over 4 to pi over 3. We get 60 degrees. If I change it to 2/3 of a pi, 120 degrees, sorry. And it's always works. So it's one, the point is it's one matrix, works for all vectors. So the matrix is the function that rotates, and it by a certain angle, and it rotates all vectors by this angle. There's just one example for what matrices can do. They can do much more. I will give you another example. Another. Take the matrix. And 1, -1, 0, 0, 1, -1, 0, 0, 1. multiply it by some matrix of a matching size, of the same size, but matches, so the multiplication will be defined. And let's calculate the product. So it also will have 3 rows and 2 columns. Okay. So the first element, I'll do it quite fast because I have a point I wish to reach here, but I'm taking the first row and multiplying by the first column. What will we get? 1 times A minus 1 times C, 0 times E. What do we get all together?
A minus C.
A minus C. And in this element,
B minus D.
yes, because we stayed on the same row, but we switched the column. So now I'm multiplying this row by this column. 1 times B minus 1 times D and 0. So it's B minus D. Then similarly here we'll get C minus E and then D minus F. And in the last row, 0 times A, 0 times C, we're just left with the third element. 1 times E, 1 times F. So we have E and F. Could you tell me what happened to the original matrix? What in words, what did this matrix do?
Assign the amount at the
Between the rows. Think of it as Gauss elimination.
It's cool.
Yeah. In words, the matrix,
Well, you got a solution.
the left matrix, subtracted each row from the row above it. That's why the third was left unchanged, because there is no row below. Agreed? So again, you see matrices being function. Again, you see, or first time you see that they can do Gauss elimination, actually. But this example is much more interesting. Why? Think of this as an image. What do I mean? A computerized image, really, of a picture, JPEG. Okay? JPEG is a bit confusing, but an actual image of a DSLR, of a camera. And why is an image a matrix? Because it's the image pixel. Right? Agreed so far? Every a digital picture is just a table of numbers. Each numbers represent the color at this specific point. Agreed? What would this matrix do to the image? Can anyone guess? I'm claiming that this matrix actually does something to an image. And I will show you also because I prepared. I'm not sure what this is. It quacks.
Does it share it?
What? Come again?
Share.
What does it mean, shear? I guess the answer is not anyway, but
Like it takes the vector space and it squishes it. Like
I'm
that.
talking about an image. I'm going to put an image of a rose into that instead of this matrix. I actually did it. I programmed it and I'll show you the results. What will happen to the rows? Okay, then I'll show you. And then I'll explain why. couple of minutes, sorry, and we'll finish. Uh, So this is the matrix. Obviously it ought to be bigger than because the image has quite a lot of pixels, but the idea is the same. Look at this called image. Show you, and then I will explain. So this is what happens. Where is the light switch? I have a light switch. Only you. Can you turn the lights off, please? Thanks. No, put it. It's the end of the lesson, so just for you to see. That's a rose from my garden. I took the picture. It doesn't matter, but I'm showing off. And and that's after I multiply by the matrix. Why did this happen? What happened? What would you say you see in the second image?
The outline.
The outlines, exactly. Why do we see the outlines? Because we subtracted rows. What happened? Not rows, rows. And we subtracted rows. And when the color is similar, the subtraction between the two rows will give 0. When the color is quite different, it will give a second number. That's exactly what we're seeing here, the outlines. The lines that mark the change between two very different colors has a whole other value than those with similar colors to them. And that shows you the multiplication of matrices actually is a lot of what Photoshop does. Okay, artificial intelligence as well, but I don't know a lot about that. But really multiplication and other operations with matrices could actually, this is called an emboss effect, could actually apply effects to pictures. Yes.
So also moved it down a little bit, right? Maybe not.
When one row versus 1,000 or
Okay, but-
720, it's nothing. You wouldn't. I wouldn't even say it moves because from each row it subtracted the next one. So I'm not sure if it's a move anyway. But yeah, that's the effect, and that's an actual live version. You were seeing the picture, but it was live on a website. I'm not sure where it is anymore, to be honest. But for once it was live, I programmed it using some. Now with ChatGPT, it's probably this inch. Okay, so enough for linear algebra, and I will meet you guys at 4 for calculus.